Hello, everyone. I am happy to introduce the paper AdaFit, Rethinking Learning-Based Normal Estimation on Point Clouds. In the point cloud processing, a fundamental task is to robustly estimate surface normals from point clouds, which plays a key role in many practical applications, such as surface reconstruction, denoising, segmentation, primitive fitting, and so on. Given an input point cloud, we can obtain a local patch around the query point by nearest neighborhood searching. Then, we fit an NJet surface model on the selected local patch by a weighted least square method. Finally, the normal is computed from the coefficient of the fitted surface. However, there are two main challenges needed to be solved. The first one is how to accurately fit a surface with the presence of noise and outliers, and the second one is how to select an optimal neighborhood size. To address the problem of noise and outliers, most existing methods use a weighted surface fitting which predicts point-wise weights to control the contribution of every point to the final surface. The focus of these works is to obtain more accurate point-wise weights that can reduce the effects of noisy points and outliers as possible. For example, DeepIDer and DeepFit utilize the network to predict point-wise weights and estimate the surface normal by a differentiable and weighted least square surface fitting. Though these methods achieve substantial improvements on normal estimation, the estimated normals are still not accurate in complex regions. The reasons are twofold. First, it is hard to precisely select a suitable polynomial order for every point. Second, such weighted least square fitting method is inherently sensitive to outliers. In the weighted least square surface fitting, we must preset a polynomial order n for every point. However, the underlying surfaces of different points usually have different suitable polynomial orders. A typical example is shown in the right figure, where we fit surfaces with different polynomial orders, and red points in the first row show that different points have different suitable polynomial orders for the normal estimation. In the second row, we show the normal errors using different polynomial orders for surface fitting, while in the last figure, we always choose their best polynomial order for different points, which substantially reduces the overall normal RMSE to 12.85 degree. Current methods always choose a constant order for all points, for example, plain in DeepIDer or 3JET in DeepFit, which results in an inconsistency between the predefined order and the suitable order of different points. Such inconsistency either results in an underfitting, which smooths out the fine details in the neighborhood, or overfitting to noise, which brings a large variance to the output normal. Meanwhile, the weighted least square fitting is inherently sensitive to outlier. By checking how the weight of every neighboring point affects the final fitted surface, we found that the output coefficients will be more affected by points that are far away from the surfaces stated by the proposition. Thus, even though the network may learn to place small weights on these outliers, a small perturbation on the weights of outliers will still lead to a significant change in the output normal, since outliers are all far away from the surface. To address these problems, we propose a simple yet effective solution that adds an additional offset prediction to improve the quality of normal estimation. Our key insight is that predicting additional point-wise offsets enables the model to adjust the distribution of the neighboring points. When the underlying surface has a different polynomial order from the predefined one, the adjustment brings more flexibility to the network to project neighboring points onto a surface with the predefined order. Though the resulted surface may not be precisely consistent with the ground truth one, the normal of the center point is much more accurate than the one estimated by the direct weighted surface fitting. Meanwhile, the outliers in the neighborhood can be offset to a position near the resulted surface, such that all points will have similar distances to the surface. Thus, in comparison with the weighted surface fitting where the weights of outliers have larger impacts on the normal, points contribute more evenly after the adjustment, which leads to a more robust normal estimation. The second challenge is how to select an optimal neighborhood size for every point to estimate its normal. Here, we call the neighborhood size as scale. A large scale containing more points provides more information about the underlying surface, but may include irrelevant points which oversmooth the sharp edges. A small scale only contains a small set of most relevant points, thus may improve the accuracy of the normal estimation, but is unavoidably sensitive to noise. The scale is a sensitive hyperparameter that requires a carefully tuning for an accurate normal estimation. To address the problem of the scale selection, we use a novel architecture design called Cascaded Scale Aggregation (CSA) layer. As shown in the figure, the CSA layer is in charge of extracting features from different scales. The CSA layer uses features from a larger scale to help the feature extraction at the current smaller scale. The final fitting only uses the points from the smallest scale. In this case, the large scale provides more information of the underlying surfaces, while the small scale includes the most relevant points for the surface fitting. Thus, the proposed CSA layer enjoys the benefits from both the large scale and the small scale, which results in an accurate surface fitting. Based on the CSA layers, we design our AdaFit network. As shown in the figure, AdaFit mainly consists of MLPs and CSA layers for feature extraction on every point. Then, two heads are used to regress the weights and the offsets. We follow exactly the same experimental setup as PNet, including train test split, training data augmentation, and adding noise or density variations on testing data. The angle RMSE between the predicted normal and the ground truth one is used as the metric for evaluation. As shown in the table, AdaFit outperforms both the traditional methods and learning-based methods in all settings, which demonstrates the effectiveness of using offsets to adjust the point set. Especially on the point clouds with density variations, baseline methods may fail to find enough points on sparse regions for the surface fitting, while AdaFit use the offset to project points to the neighboring regions for more robust surface fitting. The Opt curve of normal errors can show the error distribution. The results confirm that our approach is better at preserving details and is more robust to the noise and density variations. We show the visualization of the estimated normals. As shown in the figure, as the increase of noise level and density variations, the estimated normal directions of AdaFit almost remain unchanged, which demonstrates the robustness of AdaFit. We show the normal error map in the figure. It can be seen that DeepFitter performs better on the flattened regions, while DeepFit can better handle curved regions, but is not accurate for regions with sharp curves. In contrast, the proposed AdaFit is relatively more robust on all regions and all settings. We further provide detailed results on the sharp edges. As shown in the figure, AdaFit can predict accurate normals so that the normal directions are sharply changed on the edge. However, due to the noise, it is ambiguous for the network to determine the correct plane for some points very close to the edge, which results in a large angle error on these points. In contrast, baseline methods produce normals gradually changing on the edge so that their error is smaller on the edge, but much worse in the vicinity. To test the generalization capability of AdaFit, we directly evaluate AdaFit on real datasets including the indoor CNN dataset and the outdoor semantic 3D dataset. Note that all the methods are only trained on the PCPNet dataset and directly evaluated on these datasets. As for the CNN dataset, the RMSE of AdaFit and baselines are shown in table, and the angle error visualizations are shown in the figure. The results show that AdaFit can predict more accurate normals than baseline methods. The semantic 3D dataset contains point clouds collected by laser scanners. Since there are no ground truth normals, we only show qualitative results. The results show that AdaFit can find sharp edges on point clouds, while other methods oversmooth these normals. We visualize the predicted offsets of AdaFit in the figure. Two examples are shown in left figure, in which adding the offset prediction brings more robustness to outliers and avoids the overfitting or the underfitting. In the right figure, we show neighboring points before and after being offset. The results show that the predicted offsets will shift the blue points to the underlying surface because these blue points are far away from the surface. In contrast, the red points are almost on the underlying surface, so the predicted offsets on these red points are very small and they are almost unchanged after being offset. Accurate normals can help the Poisson reconstruction to produce a high-quality and complete surface from point clouds. We show reconstructed surfaces using normals estimated with different methods. As for the column shape, we can find the results of AdaFit is more accurate. The results of baselines will contain many artifacts. The results show that the reconstructed surfaces using the normals from AdaFit is more detail preserving than the baseline methods. We can find the results of AdaFit is more complete, especially in the crown position of the shape. The baselines all fail to reconstruct the complete results. Estimated normal can also be used in point cloud denoising, the qualitative results of denoise point clouds, and their corresponding reconstructed surfaces are shown in the figure. The results show that using the normal estimated by AdaFit for denoising produces a smooth surface in flattened regions, while still preserves sharp features on edges. Thank you for your attention.